I think we left off with if we wanted to talk about the inverse sine of x, we had to appropriately limit our domain. So if we were dealing with sine and we wanted to talk about inverse sine, how did I have to limit my domain? Negative pi over 2 to pi over 2. And y went between negative 1 and 1. Which means for your arc sine, the numbers you can plug in were between negative 1 and 1. And the answers that you get out are angles between negative pi over 2 and pi over 2. And then we went through the exact same process. Oh, we had one more thing. We'll come to that later. We went through the exact same process for cosine. We wanted to talk about arc cosine. But we discovered that in order to make cosine be a one-to-one function, we had to use a different domain. What did we have to use for a domain for cosine to be able to talk about arc cosine?
0 to pi.
0 to pi. And our y value still went between negative 1 and 1. So for arc cosine, our x values are between negative 1 and 1. And our y values are angles between 0 and pi. And then I think the final thing we did is I think we derived the formula for the derivative of the arc sine of x. What was our formula for the derivative of arc sine of x? I believe we came up with 1 over the square root of 1 minus x squared. And I don't think I derived this one, but I talked about it briefly. I'm not going to derive it. You can look it up in the book if you don't believe me. The derivative of arc cosine turns out to be negative 1 over the square root of 1 minus x squared. So I think that's where we left off. We had done, I think, pretty much everything we needed to do with sines and cosines and arc cosines. And we were ready to start talking about our other functions. All right, so let's talk about tangent. Is tangent a one-to-one function? If it's bounded, that's correct. As it is all by itself, it is not a one-to-one function. How do you bound it? Negative pi halves to pi halves, I believe is correct. Because if you look at the graph of tangent has these things. And it has asymptotes. Like so. And I believe these asymptotes do occur, that first group of them occurs at minus pi halves and pi halves. Because if we remember that tangent is sine over cosine, we're going to have cosine on bottom. Cosine is 0 at pi over 2. Cosine is 0 at negative pi over 2. So that's where the asymptotes happen. So if we're dealing with tangent, our domain is almost exactly the same as sine. The only difference is for sine we could have the equal to's in our inequality. For tangent we cannot, because we would have 0 on bottom. So our domain for tangent is almost identical to our domain for sine. How about the range? What kind of y numbers do you get on tangent? All real numbers, because this goes down forever, it goes up forever. So the range is all real numbers. So over here on our arctangent, our domain becomes all real numbers. But our range is angles between minus pi over 2, equal to, and pi over 2. Questions on that? Cotangent. How will cotangent be different?
For the arctan, would that pi over 2, would that be a y or an x then?
Yes, thank you. It's a y. Yeah, because it's range. Thank you. All right, how about cotangent? What's the graph of cotangent look like?
Just shifted over. The same as tangent is shifted pi over 2.
It's shifted over pi over 2, and instead of being increasing, they are decreasing. So the cotangent graph is shifted over by pi over 2, which means the asymptote's going to be at 0, and the next asymptote's going to be over here at pi, and the graph is decreasing. Correct. So cotangent is very much like cosine, which kind of makes sense. Tangent has pretty much the same domain as sine because tangent has sine on top. Conversely, cotangent has pretty much the same domain as cosine because cotangent has cosine on top. Okay? And then the range is still all real numbers. And so over here, when we deal with arc cotangent, your domain is going to be all real numbers, but your range, and I made sure I used y this time, your range will be angles at value between 0 and pi. Questions on that? All right, we got 2 more to go. How about f of x is secant x? Anybody remember what secant x looks like? It is 1 over cosine, which means, again, it's going to have asymptotes. It's going to have asymptotes where cosine is 0. So what numbers give cosine to be 0 again? Pi over 2 and negative pi over 2 and you go pi over 2. What's the next positive one after pi over 2? 3 pi over 2, 5 pi over 2. That's all the odd ones. All right. So we have pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. And then what's the cosine graph, or what's the secant graph look like in between the asymptotes? Well, I know that cosine of 0 is 1. And I know if I'm using angles between 0 and pi over 2, that's in quadrant 1. If I'm using angles between 0 and negative pi over 2, that's in quadrant 4. Cosine is positive in both those quadrants. So it looks like this. Looks kind of like a little parabola, but it's really not a parabola. Parabolas don't have asymptotes, but it kind of looks like that. And then over here, I'm using angles in quadrants 2 and 3, so it's an upside down parabola looking thing. And same over here. And then it flips back, it goes this way again, that way again, on and on and on forever. Okay, so for secant, how are we going to pick x values to make this function 1-to-1 and to also incorporate all of the y values that we can?
Between negative pi over 2 and pi over 2.
Now I can't go between negative pi over 2 and pi over 2 because I've got this shape. It's not 1-to-1. A horizontal line crosses it more than once.
Can we have holes in the x values?
Yes, you can have holes in the x values.
So
Not only can you, in this case, I think must you.
negative pi over 2, the 3 pi over 2 without the x value pi over 2?
Close. I don't think that's quite what you want, but you're close. I think what we want is we're going to use this piece. Is that function 1-to-1 there? Yes, but I don't get all the y values, do I? And then we're going to use that piece. So we're going to go between 0 and pi, but we've got to throw out one number. Pi over 2, because that's where the asymptote happens. All right, so secant's kind of screwy here. So for f of x equals secant x, our domain has to be x is between 0 and pi, but x cannot be pi over 2. And then what's the range? What kind of y numbers do you get? No, you don't get all of them. No, I get 1. 1's right here. And I get -1. I don't get 0, that's true.
Negative infinity to -1, and then 1 to infinity.
Correct. I don't get 1. I also don't get a half. I don't get -3/4. I don't get anything between -1 and +1. So our range is y is less than or equal to -1, which is all these y numbers, or y is greater than or equal to 1, which would be all those y numbers. All right, so secant and arc secant are kind of difficult to deal with because you get really bizarre domain and range. But that's what you get. So now that we have all that, we can talk about the inverse. Arc secant x. Its domain, the numbers you could plug into it, would be numbers less than or equal to 1, or numbers bigger than or equal to 1. And the range, the angles you get, would be between 0 and pi, but you could not get pi over 2. Questions on that? Finally, our last exciting graph. G of x is cosecant x. Well, what I noticed up here for secant, this was exactly the same as it was for, what's that domain the same as? Cosine, except I have to throw out 1 point. So it would make sense that cosecant should have the exact same domain as sine, except I need to throw out 1 point. Which point do I need to throw out? 0, because sine of 0 is 0, and then cosecant would have 0 on bottom. So my domain is going to be negative pi over 2, less than or equal to x, less than or equal to pi over 2, but x cannot be the number 0, and my range will be exactly the same. Because the secant graph and the cosecant graph have really the same pictures. Again, they're just shifted. So you're going to have the same y values. They're just going to be moved over more and moved over more, that's all. All right, so to talk about our arc cosecant, G inverse of x is arc cosecant x. We're going to have x could be numbers less than -1 or numbers greater than or equal to 1. And our range is all these angles between negative pi over 2 and pi over 2. except we'll never get the number 0. Questions on that?
Can you go back to the arc cotangent?
Yes, I can go back to the arc cotangent. That one? So for arc cotangent, your domain is all real numbers. Your range is your angles between 0 and pi. Right. Of all those domain and ranges and all that stuff, which ones do you need to know?
Sine and cosine.
Sine and cosine are the ones you should really worry about. I wouldn't worry about memorizing the domain and range of secant and cosecant. Tangent, arc tangent comes up sometimes. I think we'll see an example of that later today, but we won't need to worry about our domain and range. You should really know the domain and range of the arc sine and the arc cosine. Those are the two that will come up a lot. All right, so derivatives. If y equals the arc tangent of x, I'm going to do the same sort of trick I did for arc sine. I'm going to derive the formula for arc sine or for arc tangent, and the way we did it is we applied the tangent function on both sides. So tangent of y is x, and then we took the derivative. What's the derivative of tangent? Secant squared. So we're going to have secant squared y prime equals 1. So y prime would be cosine squared of y, because secant squared is 1 over cosine squared, so I can multiply both sides by cosine squared. But again, while that's a nice answer, that's not really the answer I want. I really want x's over here on the right hand side, because this is dy dx. Usually we write our answer with x's. So how am I going to get x's here?
Plug in right hand through y.
True, I could just plug in arctan of x. So I could write this, although I don't like this answer much better. This is cosine squared of arctan of x. That is a correct answer. Not the answer I wanted, though. Here's what I'm going to do. I'm going to draw myself a triangle. Here's my angle y. And this is a right triangle, of course. And I know tangent of y equals x. If tangent of y equals x, how would I label my triangle? Opposite over adjacent. So think of this as being x over 1. That's x, and that's 1. I go talk to my good friend Pythagoras. That third side would be, the hypotenuse would be the square root of 1 plus x squared. So now I want the cosine of that angle. There's my angle. I want the cosine of it, and then I want to square it. So what's the cosine of this angle? 1 over the square root thing. But then I square it. What happens when I square it? The square root thing goes away. So the derivative of the arc tangent of x turns out to be 1 over x squared plus 1. And for some reason, it's usually written as 1 over 1 plus x squared, which always struck me as odd, because in every other situation we put the x squared first, we put the numbers later, but it's almost always written that way. I don't know why, but it is. Questions on that?
Wolfram alpha always does.
Wolfram alpha writes it that way?
If you do x squared minus 1, it'll be like negative 1 plus x squared.
Yeah.
It's weird.
Yeah, I don't know why it's programmed that way. Okay, you could do the exact same trick, and you would discover that the derivative of arc cotangent x is minus 1 over x squared plus 1. And the only reason you get a minus sign is because if you come back up here, if you have cotangent instead of tangent, what's the derivative of cotangent? Negative cosecant squared. That's where that minus sign comes from. Otherwise, the whole problem works exactly the same. And then the last two. I'm not going to derive the formulas for these two. You can trust me, or you can look it up in the book. The derivative of arc secant of x turns out to be 1 over the absolute value of x times the square root of x squared minus 1. So I want to make sure that I have that one right. Doing it from memory. Oops, clicked on the wrong button. I'm very sure I do. I do. And the derivative of arc cosecant of x is negative 1 over absolute value of x, square root of x squared minus 1. So what's the good news about the derivative of these arc functions?
You don't have to know how to do them.
You don't have to know how to do them, that's correct. What else is good about them? They're the same except for the signs. The derivative of arc secant and the derivative of arc cosecant are exactly the same, except one's a positive, one's a negative. The derivative of tangent and arc tangent, exactly the same. One's a positive, one's a negative. And sine, arc sine and arc cosine, they were exactly the same. One was positive, one was negative. So that's the good news about them. Alright, so I'm going to pick, this is why I wanted to bring the book today, but I forgot it because I wanted to pick some homework problems out of the book. So I got to go on the computer and look them up here. So this is problem 49. It has y equals 2x arc cosine x minus 2 times the square root of 1 minus x squared. And it would like us to find the derivative. What am I going to need to do to find the derivative of 2x arc cosine x? I'm going to need the product rule. All right. So I'm going to take the derivative of the first one. The derivative of 2x is 2. And I leave this one alone. Arc cosine x. Plus, I leave that one alone, 2x. And then I take the derivative of arc cosine x. You probably haven't memorized it yet. It's negative 1. That's negative. Very good. Divided by square root of 1 minus x squared. So that's a fact that you will eventually memorize. Minus. Then I have to take the derivative of this thing. What do I have to use to take the derivative of that piece? The chain rule. So I'm going to have the 2. I'm going to have 1 minus x squared to the negative 1/2, because I think of square root as being a 1/2 power, multiplied by the derivative of the inside. The derivative of the inside is negative 2x.
From that to an up,
Yeah.
you go with because you brought down a 1
Yeah.
half.
Oh, and I brought down a 1/2. Thank you, yes. There it is. There's the 1/2 I brought down. Got to write that. Although you don't have to simplify your answers, I'm going to simplify. This is 2 arc cosine x minus 2x over the square root of 1 minus x squared. And then here I've got those reduced. I've got a minus and a minus. That's a plus 2x over the square root of 1 minus x squared, because that negative 1/2 is a square root on bottom. And something kind of cool happens. Those cancel out, and you're left with the derivative of that ugly function that we started with turned out to be 2 arc cosine of x. Questions on that?
Are we really going to need to memorize the derivatives of arc of all those functions, or are we going to be able to have like a formula sheet?
Formula sheets? You want formula sheets? I'll think about it. I'll get back to you on Monday. Other questions?
Where are we getting that review back in?
I'll get back to you. I should have a review for you on Monday. What's the integral of 2 arc cosine of x?
2x over cosine of x minus 2 root x, or root of, yeah.
2x arc cosine x minus 2 square root of 1 minus x squared
Let's see.
plus c.
All right, so, or if I really wanted to, I could divide everything by 2. And then we just found an integral formula for the arc cosine. There's the integral of arc cosine. So the big question is, if somebody didn't give you this screwy formula from the beginning and you took its derivative, how in the heck would you come up with that screwy formula in the first place to know that that's the integral? See Chapter 7. We will learn a technique, something called integration by parts. This is an integration by parts problem to get that answer. Whatever that means. That's what it is. All right, let's try another one. How about y equals x arctan of 2x minus 1/4 natural log, and the natural log's in a few days, 1 plus 4x squared. That's a minus 1/4. That's correct. Minus 1/4 ln of 1 plus 4x squared. All right, once again, to take the derivative of this piece here, what are you going to need to do? Product rule. So y prime is, you take the derivative of the first one, that's a 1. You leave arctan 2x alone. Plus, you leave the first one alone, that's an x. And then you have to multiply by the derivative of arctan of 2x. 1 over x squared plus 1. That's if you just have an x there. What's going to happen if you have a 2x there? So you're going to have, normally our formula is 1 over 1 plus x squared, but if we have a 2x, then we're going to have to take the 2x and square it, so you're going to have a 4x squared. And then you need to use the chain rule, which tells you better multiply by 2, the derivative of the inside. All right, so there's a chain rule problem right there. Minus 1/4 times. What's the derivative of ln of 1 plus 4x squared?
1 over 1 plus 4x squared times 8x.
1 over 1 plus 4x squared, and then you have to take the derivative of the inside, which is 8x. Questions on that? All right, so do you see how clever your author is being here? Look at these two pieces. What can you tell me about those two pieces? They add up to 0. So what do we get? Arctan of 2x. So once again, what we just did in actuality is we just found an integral formula for arctan of 2x. There's the integral of arctan of 2x. And again, that's an integration by parts problem, whatever that means. Questions on that? What's that? You looking forward to integration by parts?
Well, I started looking up and slowing down.
Do we have to know those integrals for right now?
Absolutely not. No, you do not need to memorize those integrals. In fact, I would say there's no point in ever memorizing those integrals. I don't know them. I don't have them memorized. If I need them, it's very, very rare that they come up in the first place. But if I ever need them, if I have to, I can derive them. But most likely, I grab a reference manual and I look them up. Those are not integrals that come up very often. Not in my experience anyway.
What's the application of this? Like, what kind of graphs do you get from that?
What's the application of this? I'm so glad you asked. All right, so this is page C74, number 91. Here's the basic setup. You have an airplane 5 miles in the air, and it's flying in that direction. And you've got a person standing here observing, and you're looking at the angle of elevation called theta. First thing it asks us to do, it asks us to write the angle theta as a function of x. So what can you tell me about theta in x?
It increases, x decreases.
That's true. As theta gets bigger, as this angle goes up, the airplane's going that way, so x is getting smaller. Tangent of theta is 5 over x, right? Because tangent is opposite over hypotenuse. So write theta as a function of x, we would write theta is tan inverse of 5 over x. So this is where these inverse tangent functions start to come into play. Then it says, the speed of the plane is 400 miles an hour. I want to know d theta dt when x is 10 and when x is 3. All right, so I find the derivative, d theta dt equals, what was our formula for tan inverse again? 1 over x squared plus 1, except we're not going to have x, we're going to have 5 over x. So it's going to be 1 over 5 over x squared plus 1. But then I need to multiply by something.
5.
Not 5, but you're on the right track.
Negative 5. No, yeah. Negative 5x is negative 2.
Negative 5 over x squared. Where'd you get negative 5 over x squared?
Because 5 over x is the same as 5x to the negative 1.
Correct. We've got to use the chain rule. We're thinking of this as 5x to the negative 1. We bring the negative 1 down, subtract 1 from our exponent, that's negative 5, x to the negative 2. Times, not done yet. Notice over here, we did d theta dt, not d theta dx. If we had done d theta dx, that would be the derivative, but we did d theta dt, so what do we need over here? We need a dx dt. We are differentiating everything with respect to time. So we need a dx dt. Now it's just a matter of plugging in our numbers. So when x equals 10, d theta dt is 1 over 1/2 squared plus 1 times negative 5 over 100 times, what's dx dt? 400, close. Negative 400. Why negative 400? Because it's flying towards the observer. The distance is getting shorter. The distance is decreasing. So the derivative is negative. You grab your calculator, you type that up, that gives you the answer, and then you repeat when x is 3. When x is 3, you're going to have d theta dt equals 1 over 5/3 squared plus 1 times negative 5 over 9 times negative 400. What would your units be on that? Not miles per hour. The speed of the airplane is in miles per hour. Radians. You're getting closer. Theta is measured in radians. T is measured in hours. So the units would be radians per hour. Not a common unit, but that's what it is for that problem. The units there are radians per hour. Questions on that? You have a billboard 85 feet wide. The billboard is 40 feet, so I'm not drawing the scale here, that one's got to be longer. 40 feet off the road, and you're driving up the road, so this distance is x, and this is your viewing angle, theta. And so the question says, a billboard 85 feet wide is perpendicular to a straight road, so that's a right angle, and 40 feet from the road, so we're 40 feet from the road. Find the point on the road at which the angle theta subtended by the billboard is maximum. I like that word, subtended. That's not a word you get to use every day. Okay, so basically, we want to make this angle right here, this angle theta, we want to know where along this road is the optimal viewing point. Where does the person have the widest angle of view, and we're guaranteed they can see as much as possible, they can see the entire billboard. Any ideas?
Find the angle of this smaller triangle, use that as a reference angle.
All right, so I'm going to call this angle right here. If this one's theta, then we'll call this one. You want to see what I'm drawing too? All right, now you can see. All right, so if this is angle theta, then this angle, we'll call that one angle, what? Phi? All right, phi. That one's phi, I believe. So what I really want to do is I want to get a function. I want to maximize theta, right? So what do I want? I want a function for theta that involves the letter x, and then I want to be able to take derivatives. All right, so any ideas? I could find the hypotenuse of this one using the Pythagorean theorem. I could. I don't think that's particularly helpful, though, because that triangle there is not a right triangle. Let's start with the easy little right triangle here. What can you tell me about x? and this angle phi that we drew? Tangent of phi is 40 over x, which is the same as saying phi is arc tangent of 40 over x, okay? Now let's look at the big triangle. And what I mean by the big triangle is this triangle that has that hypotenuse, that side, and that side. What can you tell me about that triangle?
The angle is phi plus theta.
Okay, so tangent of phi plus theta equals 125 over x, which is the same as saying that phi plus theta is arc tangent of 125 over x. So here we go. Here's our function, I think. Our function is theta is arc tangent of 125 over x minus arc tangent of 40 over x. Right? Because I can take this equation right here and I can just subtract phi, and then I can use the fact that phi is that. So there's my function. There's my function theta that only has the letter x in it. So now in theory, if I want to find the maximum, all I have to do is find the derivative and then do what to the derivative? Set it equal to 0. That will give me my critical point, and then make sure I do have a maximum. All right, so let's find the derivative. Theta prime is, all right, so our arc tangent, again, our formula for our arc tangent was 1 over this thing squared, 125 over x squared plus 1. And this time I am doing d theta dx. Then I need the derivative of 125 over x. That's negative 125 over x squared. Minus, I take the derivative of this one. That's going to be 1 over 40 over x squared plus 1 times negative 40 over x squared. All right, now comes the fun. How do you take that equation right there, one of the uglier equations you've probably seen in a while, and set it equal to 0 and solve? You use Wolfram alpha, that's correct. Or your other option would be, maybe not quite as quick and easy, you type this into your calculator and you find where it crosses the x-axis. That would be another way to do it. I am not going to take the time to try to solve that equation by hand. I don't think it's as bad as it really looks, because if I set this equal to 0, I think the first thing I would do is I would multiply everything by x squared to get rid of those fractions. And then I think I'd multiply by another x squared to get rid of those fractions. And then I'd see where I was. You could do it by hand. It's just a mess. Not a lot of fun. Questions on that?